Okay, guys, this is the solution for design problem number two, the incinerator. I asked you to look over it, try to work it out, and I told you I'll post a solution over the weekend. Well, that's today. So I want to run through that, and hopefully from the sheet you were able to figure it out. Again, I want to keep things simple, but I just kind of want you to look at the steps of going through using your KMAP tool, your truth table, and other um, ideas and concepts we talked about to solve basic problems for the PLC. So if you have the handout, Design Practice 2, Flame Detection Logic for Toxic Waste Incinerator, I'll just go ahead and read the problem statement, and you have the document with the picture on it. Design a flame detection program for a toxic waste incinerator. The intense heat of the fire is intended to neutralize the toxicity of the waste introduced into the incinerator. Such combustion-based techniques are commonly used to neutralize medical waste, which might be infected with deadly viruses or bacteria. So long as the flame is maintained in the incinerator, it is safe to inject waste into it to be neutralized. If the flame were to be extinguished, however, it would be unsafe to continue to inject waste into the combustion chamber, as it would exit the exhaust unneutralized and pose a health threat to anyone in close proximity to the exhaust. What we need in this system is a sure way of detecting the presence of a flame and permitting waste to be injected only if a flame is proven to be by the detection system. Several flame detection technologies exist: optical, which is detection of light; thermal, detection of high temperature; and electrical conduction, detection of ionized particles in the flame path, each one with its unique advantages and disadvantages. Suppose that due to the high degree of hazard involved with potentially passing unneutralized waste out of the exhaust of this incinerator, it is decided that the flame detection system be made redundant, so that failure of a single sensor does not lead to emission of toxins out of the exhaust. Each sensor comes equipped with a normally open contact. So it's normally open if no flame, it's closed if a flame is detected, which will be used to activate the inputs of the logic system. So here's the actual problem statement. Design the system so that the valve is commanded to open if and only if any 2 out of 3 sensors detect a good flame. In this way, any single failed sensor falsely showing flame could not keep the valve in the open position. Rather, it would require 2 or 3 sensors to be failed in the same manner, a highly improbable scenario for this dangerous condition to occur. They give you switch A as the optical sensor, switch B, the thermal sensor, switch C as the ionization sensor, and they refer you to figure 1, which is a diagram of the system. So going through our steps, which is similar to what we did for design 1, they want us to list inputs and outputs along with their addresses. So in the actual PLC program, of course, you would have many more inputs, but it's always good to have some kind of map or some kind of list of those input sensors, output sensors, and so forth. So there's no right or wrong way to make the list. I just made my inputs, got optical, you have a thermal, and we have an ion sensor. Let this one be A, B, C. So here are my inputs. And then you add the addresses. We'll just make up something. And then the output. Actually, this should be singular in the list is input and output because it's a list. So our valve, and I gave that output address of, so your list might look something like this. Then they say, all right, well, design the truth table. Use page 3, so they gave you a sheet, a blank sheet to write your truth table. But before you design the truth table, they want to know how many rows are required. Well, there's 3 inputs. Remember the number of rows in the truth table. Number rows is 2 to the nth power, where the n is the number of input variables. So I have 3 input variables. I need 8 rows. So statement of problem number 2, you need 8 rows, and then they want us to design the 8-row truth table. So anytime you have more than 8, it's just a matter of keeping it neat. So we'll design our truth table, our inputs, A, B, C. Somebody asked a good question in the last class. They said, all right, we go out another variable, 4, so we have 16 rows. Then over here, what you would do is repeat. You have 8 zeros, 8 ones, and so forth. It's always a power of 2. And I wouldn't give you anything larger than that, because it's just, you don't have the time to do anything bigger than that. But anyway, our truth table looks like this. And then what we want is a case where any 2 of the inputs are true. So that's going to be here. We got 2 true here. B and C are true. And then we got 2 here. We got 2 here. Now this case right here, of course, it makes sense to include that case because all 3 sensors are yelling, hey, there's a flame. So we got that case. And then so this one, I got a 0 there, 0, so I nod it. And then that one, I got a 0 there, so I nod it. And then that one, 0 there, so I nod it. And this one, I don't have any zeros. So some of you can probably just look at this and tell how this is going to end up. Again, I on purpose made it simple. I'm not really worried about complexity. I want you just to see how to use your K-map tools and your truth table tools. So this is the way you would determine the expression. So now I know that my Boolean expression has 4 terms. And make sure you can see that it's kind of cut off. So you can see that in the camera. So this one right here is knotted, and then B is knotted, and then C is knotted, and then none of those are knotted. I write the binary value of each one of these. Here I got a 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And so there's my Boolean expression, which is number 3. It says determine the Boolean expression from the truth table. Now number 4 says write a well-documented logic program developed from the Boolean expression. So we want to use this. We don't want to use this one. Of course, we want to minimize it. We don't want to use a complicated expression. We want as few inputs as possible. So hopefully that was clear. The implication was to minimize. It didn't really state to make the K-map, but in all these, it's the purpose of the K-map. So we'll go ahead and map this expression, and then we'll write the final program. So I got 3 inputs, 8 cells. It's been a little while since we K-mapped, so remember your numbering here. So I got a 1 at 0, 1, 1. So 0, 1, 1 is right here. 1, 0, 1. 1, 0, 1 is right here. 1, 1, 0 is right here. And then 1, 1, 1 is right there. So they're all kind of clumped together, which makes it nice. This is the easy one right here. I'm moving this way, so of course C is going to drop out. So I'm done with that one. Then I can share that one. Somebody asked a good question. I think they text me. How many times can you overlap a bit or a member? You can as many times as you need. There's no limit. So I'm moving up and down. B is going to drop out there. And then the last one. And of course, if you follow the pattern, you see A is going to drop out. So the minimized expression from this is the valve is going to equal B, C, or A, B, or AC. And I just want to make sure the camera's picking that up. So there you go. Pretty simple, I hope. None of this stuff is particularly hard, unless you go to higher dimensions. I mean, like we could add a 5th variable, and I can show you the K-map for that. But it looks like a Rubik's Cube. There's actually a couple ways to do higher order K-maps, but I don't know. Some people think they're fun, some people, but it's better than doing it with Boolean algebra for sure. So anyway, the program, you can see now, it's just and BC, AB, AC, and there's my valve. And I think that's, they tell you to implement your program in the PLC simulator. So put it in your simulator, design the program, and check it out. Normally when we're face to face, I give a little credit for that, but we're pretty much done with the semester, so we'll call it done. And so guys, that's it. Hopefully that was very straightforward. If you have any questions though, feel free to text me, or we'll be starting class later today. You can ask me if there's something that you don't see or follow or that you're wondering about. So there's a solution to design, program design practice 2, and I'll see you guys later when we start class in a couple hours. Thank you.